Hey, and welcome to this lesson on the similarity in right triangles. First, let's just review what an altitude is. An altitude in geometry, the altitude of a triangle, is a line segment that goes through the vertex. So the vertex is a point on the triangle. So we have a vertex, in this case E. Then the line segment that goes through that vertex to the opposite side of the triangle, or the base of the triangle, and forms a perpendicular angle, or a right angle, one that's 90 degrees. That is an altitude. That red line H is an altitude. Sometimes it's also referred to as the height of the triangle. There's a special type of similarity that takes place when an altitude of a right triangle is drawn. So the altitude to the hypotenuse of a right triangle, so that's an altitude from the vertex of a right triangle. In this case we have triangle ABC. It's a right triangle. The altitude from vertex C is dropped, and what it does is it divides the triangle into two smaller triangles, ACD, which is drawn down here for you, and BCD, which is drawn down here for you. It separates, it divides the triangle into two triangles that are similar. So these two smaller triangles are similar to each other, and both of those triangles are also similar to the original triangle ABC. So triangle ABC is similar to triangle ACD. Triangle ABC is similar to triangle CBD. And triangle ACD is similar to triangle CBD. Now notice the ordering of the letters. That is very important to which sides are corresponding and equal in ratio. Now we're going to talk about what's called a geometric mean. First, let's look at proportions. The first and last numbers in a proportion, in this case A and D, are what are called the extremes. The means are the inner two, so B and C, the two in the middle. If we were to write out the proportion, we would have A to B is equal to C to D. So the two outside portions are called the extremes. The two insides are called the means. So again, in this case, A and D are the extremes. They are the first and last numbers in the proportion, and the two middle numbers are B and C. Frequently, the means of proportions are equal. If the means are equal in a proportion, that's what we call a geometric mean. So the geometric mean of two numbers, let's say the two numbers or the two extremes are A and B, the geometric mean for those two numbers is the value of x that makes this proportion equal. For example, if I wanted to find the geometric mean of 8 and 2, I would set up the proportion 8 over x equals x over 2. I would cross multiply. Sorry, this step is supposed to be 16 over x equals x. It's not supposed to be there. But ultimately, if I cross multiplied, I would get 16 equals x squared, and I end up with x equals 4. And I can look over here, and if I substitute 4 into the original proportion that I had with x, I see that I do get, if I simplified those two ratios, I would get 2 equals 2. So that proportion is true. So the geometric mean of 8 and 2 would be 4. there are two corollaries. A corollary is an extension to a theorem. So we just had that theorem about similar triangles when an altitude is drawn. Now this corollary is going to help us apply that to certain problems. The first is that the length of the altitude, so in this case CD, the length of the altitude to the hypotenuse is the geometric mean of the lengths of the segments of the hypotenuse. For example, we have AD and DB. So those are my two extremes. The length of the altitude CD is the geometric mean. So that goes right here. So if I look at this example, the altitude, so the length of the altitude is my geometric mean. So that goes in the middle of the proportion. And then the two new segments that are created when the altitude is drawn are my extremes. So 2 over 4 would equal 4 over 8. And my next corollary is that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Now that probably was a lot of mumbled words, but basically what it is saying is that the base here, AB, and this base, AD, are the extremes to a proportion where AC is the geometric mean, and CB is also the geometric mean if I took DB and the length of AB. So for example, if I have 2 here, the segment of the base that is adjacent to it or next to it would be one of my extremes. The whole base itself would be one of my extremes, which is 4, and 2 would be the geometric mean of the 2 lengths. And so if we went through a problem real quick, we wanted to find what are the values of x and y. Well, I see y has the hypotenuse, or I'm sorry, the altitude. So I'm going to use the first corollary, and I'm going to say that 4 over y is equal to y over 12. So I would set up that proportion. Then I would simply solve for y. I would cross multiply and get y squared equals 48. Take the square root of 48, and if I simplify the radical, I get y equals 4 times the square root of 3. X is one of the sides, so I would take the whole length of the base, which is 4 plus 12, as one of my extremes, and I would take 4 as my other extreme, and x would be my geometric mean of those 2 lengths. So I would write the proportion. Again, I would cross multiply. 4 plus 12 is 16. 16 times 4 is 64. So I would have x squared equals 64. If I take the square root of both sides, the square root of 64 is 8, and therefore x would equal 8.